So you run into functions that do not have antiderivative really based on substitution and all that. And so when that happens, then all of a sudden you have a little bit of an issue because you can't just, like for this guy, I could do a u, but then I have this major problem here because I'm going to have, even if I have a u with this one, I'm going to have a u minus 1 over negative 1, and then I'm going to take that to the third power. So I have two very complicated functions put together, and none of them are going to just easily substitute out. And so we use the Trapezoid Rule and the Simpson Rule to estimate it. And it's based off the same concept as the derivative. Derivative is rectangles, right? Whereas the Trapezoid Rule uses, albeit trapezoids, right, to estimate. And so it's from that thought that you take, the height divided by 2, base 1 plus base 2, and just that's where they get it from. The formula itself is listed at the top of page 301. We have F is continuous on AB, the trapezoidal rule for approximating this antiderivative is B minus A, so your top limit, your upper bound minus your lower bound, and then over 2 times n. It will tell you how many trapezoids it wants you to do. So typically it'll be like 4 trapezoids or 8 trapezoids, and it'll actually say the number. So that is what the n is. And then you set up this, if you have n trapezoids over that length of space, then each trapezoid is going to be a certain width. And so you kind of walk from the starting point to the ending point based on how wide they are. So let's look at the first one. Of course, they give us a trig one as the first one because, that's good times. All right, so the first thing we look at is that sine of x cannot easily be derived, all right? Because if I take sine of x as the antiderivative of sine of x, we don't really have at this point. And so I have an issue at this point in my calculus life with taking the antiderivative of sine of x. We know what it is once we've memorized it, right? Which is just negative cosine. But at the same time, they're using one that we have knowledge of, right? And so if you get to this point and you know one, you're just going to do it. They're not going to give you ones you know. They're using this so that you can see what it is if you actually take the antiderivative of it. And so if you came upon something and you're like, I haven't learned sine of x antiderivative, then you have an estimation, all right? And so for this one, they've given us one, okay, we know the antiderivative, we're going to do the trapezoid rule, and then we're actually going to take it and compare it to what we know it to be and see how close we get using the trapezoid rule. And they actually do it with 4 and then with 8, so we can see which one you think will be closer. Likely the 8 is going to be closer to actual because it's more trapezoids, less room for error, okay? And what's nice about the sine graph and the cosine graph, which we've both done the antiderivatives for, is that you have this natural curve, which trapezoids are nice for because, you can see in the picture that the curve itself is nicely done. So we're going to do this using the trapezoid rule. Our b then is pi. So we have pi minus our a, which is 0, over, and we're going to start with 4. All right, and for the trapezoid rule, there's 2 things that you do. One, you figure out the width, so how far apart they are, and then you figure out what goes in front. So if I want to find the change in x, or how far apart they are, I'm going to use the number that I have, and that's 4. So this is just going to be pi over 4, which means that every single trapezoid is going to be pi over 4 width, okay? Now, that's not what you use in front of your rule. In front of your rule, you use b minus a over 2n. So don't get confused with the width of each trapezoid and what you put in front, okay? So what we're going to put in front is we're going to put the b minus a over 2 times the number that I have. So that's going to be pi over 8 in front. So we're going to have pi over 8 in front. And then we are just plugging in walking from one point to the next. So we're going to start at 0, and we are going to walk all the way to pi, all right? And our widths are going to be pi over 4. And so we're going to say, well, I'm going to start at 0. The first one's going to be pi over 4. The second one's going to be 2 pi over 4, which is pi over 2. The third one's going to be 3 pi over 4. And then I wrote him a little too far out, but then I will be at pi. All right. Now you'll see that I have 5 things that I'm going to have to use for my trapezoid rule. Because now the rule says, well, you're going to do this, and you are going to take it and you're going to plug it into that function you've been given. So we're going to plug in f of 0. We're going to plug in f of pi over 4. We're going to plug in f of pi over 2. We're going to plug in f of pi 3 pi over 4. And scooch it over a little there. We're going to plug in f of pi. All right. On top of that, the trapezoid rule has another thing. You multiply the inside guys by 2. So all of the outer ones, whatever's first, whatever's last, that's just going to be itself. But the trapezoid rule says everything in between, you're going to multiply by 2. And so you have to put your 2's there.
Serves as a coefficient.
For this one, I am going to take the actual function and plug it in. So I'm going to keep my pi over 8 out here.
So you don't integrate at all.
So f of 0, well, sine of 0 is 0 times 1 is just 0. Sine of pi over 4 is square root of 2 over 2 times this 2. So I'm just going to get square root of 2. Sine of 1 of pi over 2 is 1. So 1 times 2 gives me 2. Sine of 3 pi over 4 is also square root of 2 over 2. So this is just going to be square root of 2. And then sine of pi is 0, right? Times 1, which is also 0. All right. And so if we were to put this into a calculator, we would do 2 plus 2 square root of 2 times pi divided by 8. So we have to multiply by this pi over 8 out here. And we are going to get approximately 1.896. All right. If you were to do this with 8, all right, I'm just going to set it up for you so you can see it. If I did this with 8, a couple things would change. Instead of my division, my walking being pi over 4, it would be pi over 8. And out here, I would actually have pi over 16, okay? And then I would say, well, I need the sine of 0, right? And then I need 2 times the sine of pi over 8, right? Because I'm going in eighths now. And then 2 times the sine of 2 pi over 8, or pi over 4. And then 2 times the sine of 3 pi over 8. See what's happening here? Right? And then the sine of 4 pi over 8, which is just pi over 2, and so on and so forth. And you would do that all the way until you get to the sine of pi at the end there. And that is your approximation. And when you do that guy, you get 1.974. Okay? Now, let's see. We actually know antiderivative sign, right? So we were pretending, hey, in this point we don't know how to do this, but we actually do know the antiderivative sign, okay? And so because we know this guy, we're going to actually do it and see how we did. So if I were to take integration from 0 to pi of sine of x dx, I know my integration of that is negative cosine, right? Because just how it works with derivatives. So negative cosine from 0 to pi, right? It looks like it's moving towards something in particular, does it not? What does it look like it's moving towards?
It looks like it moved towards.
So this is my first with only 4. This is with 8. If I were at 16, it'd probably be 1.995 or something, you know, if I were to do 16. I know that right, so I know that I have the negative cosine of pi minus the negative cosine of 0. Negative cosine of pi Well, cosine of pi is -1 times negative is 1. The cosine of 0 is 1, so I have minus a negative plus 1. So I know the actual antiderivative here is 2. And so you can see these are valid approximations. While they're not exact, they're valid. So you're going to come across one, and even if there is a method to do it, if you haven't learned it yet,
So after
you can use it. Well, and I will say, it will say use trapezoid rule, and it's likely going to be ones that you cannot do without, you know, I mean, this was one they gave you so that we could actually plug it in and show you what it actually is, which is a little bit nice. But the next one they give us is actually one that we can also do. It's the same one. We're just doing it with the Simpson rule. And they're doing this so we can see that what you'll see with Simpsons is it is sometimes a closer approximation. It really just depends on the function. This one got with, I think they do it with 4 and with 8. And they get pretty close. I think the Simpsons actually gets a little closer when we do it with the Simpsons rule, but the Simpsons rule is very similar to the trapezoid rule. Conceptually, it's similar. Simpsons rule. They do the same thing. They do b minus a over 3n now. So now we're making our, what we're multiplying by just a little bit smaller. And then you'll notice that the first and the last are still the same, 1 and 1. But on the inside, you start with 4, 4, 2, 4, 2, and you keep alternating until you get to the end. And so you basically alternate your coefficients between 4 and 2 for your center guys. And again, as it says right here, as n, or the number of trapezoids that you have, approaches infinity, you'll find that the right-hand side approaches the actual approximation. So if I were to do that same exact one with Simpson's rule, the only thing different here, so let's say I want an n of 4. The only thing different, my spacing would be the same, but I would have b minus a, so pi minus 0 over 3 times 4. So I would put this over 12. And I would still do the sine of 0 plus, now I'm going to say 4, sine of pi over 4, plus 2, sine of pi over 2, 4, sine of 3 pi over 4. The last guy does not have anything, right? And when you work that all out, you actually get 2.005. And when you do it with 8, for n equals 8, you're going to get 2.003. You see that it's moving the opposite direction, but also towards 2, right? We're also moving towards 2. So if we were to continue with the number, you would see it move closer and closer to 2, just like we did limit theory at the very beginning of this chapter.